Hey, afternoon, folks. This time around, I'm coming with the Pythagoras theorem. The idea here is to try and quiz you to say where exactly could have this theorem originated from. This theorem is important because we use it quite often in trigonometric problems. So it was very, very key for us to understand exactly where Pythagoras could have drawn his reasoning from. So what I'm going to do today, I'll try and prove that that theorem is really true. And after that, I'll then try and see how basic two trigonometric problems can be proven as well to be true using the thinking that we get from the Pythagoras theorem. So without further ado, let's start. That's the Pythagoras theorem. Let me write here Pythagoras theorem. Now, this theorem is handy. What it says simply says, given a right angle triangle, a squared plus b squared is equal to c squared. And when I say right angle triangle, we are talking of a triangle where one of the interior angles is 90 degrees in size. And from this triangle, we have got vertices that we will denote in capital letter form. So I've got A, B, and C. But the corresponding sides to a vertex, they are denoted in small letter form. Opposite C, we have small letter a. Opposite vertex A, we have small letter a. Opposite vertex B, which is this side, we have small letter b. So that's where the theorem was drawn from. But the thinking that I want to show here is going to use shapes called rectangles. No, in particular, this is going to be a special rectangle, which is a square. So I'm going to draw a square for you guys to say, given a square, but I'm going to use two identical squares, which are going to be of length a plus b. So the length of this square is made up of a plus b. But remember, on the top part, we said the theorem, it originated from a right angle triangle, where if we have a triangle with side B here, side A, and C, we are saying it follows that if it's right angled, then A squared plus B squared equal to C squared would hold. So let me try and play around these shapes. What I want to do on both shapes, I want to place the dimensions A and B. But because they are squares made up of length A plus B, let's see. If I alter sequentially that at a certain point, let's mark A, then we have B. Then I come this side, at a certain point, I mark A, then I have B. Again, I'm just altering these dimensions like this, A, B. I think one would agree with me that this is a square where each of these angles are going to be 90 degrees in size. But now I'm going to go to the other shape with the similar dimensions, but I'm just going to rearrange the lengths A and B. Let me think to say this is length B, this is length B. So if this is length B, it means we expect this to be length A. Same applies here, we expect this to be length A. And when I come this side again, I expect this to be length A and there to be length A. So this will be length B and length B. Now, let me try and build right angle triangles within these two squares. One would agree with me that from the right angle triangle that we built initially with lengths, sorry for that, let me drop it a bit, with lengths B, A, and C. If I'm to try and imagine those shapes in in the two space that I have, I'm allowed to join this point here to this marking, and it builds me a triangle, this triangle which is similar to the one that I have, such that this becomes a dimension C. And if I do the same there, I'll call this length C. Then I do the same because this is A, this is B, so I can connect and I call this side C as from the picture that I'm seeing of the triangle. Then finally I have one there. So I managed to come up with, if I'm to count, is 1, 2, 3, 4. right angle triangles from the square of length A plus B. Let me come this side and look at the picture that I have here. This picture, I don't know, I'm seeing that from this point and that point, I've got small adjacent sides of equal dimension, such that if I'm to think of joining points, what it means if I go this length A and that length A, it means I've got a square, which is going to be of area A squared, because all the sides they're equal. Similarly, if I go up here and go that side, because opposite sides of a rectangle, they are equal in length, means this will be of length B. Same applies, this will be of length B. So if I target this shape here, it's going to be a square of dimensions B all over. So its area is going to be B squared. Now, what do I do with the remaining spaces? If I bring a diagonal, like, let me bring a diagonal whichever way, like this, then in this triangle, it's AB, it means this length will be C. Similarly, this is A, and I have B here, that will be C, which is common. So it's another right angle triangle because they are adjacent on a straight line. When I come this side, I do the same. If I just go this dimension, I have A, I have B, so it means the longer side is going to be C. And we can see clear that in this other triangle, this is also 90 degrees, so I have A, B, and that will be C. So what's the quiz? If I count, it's 1, 2, 3, 4 triangles that I have in both shapes, such that in the first shape, if I'm to remove triangle number 1, I also remove triangle number 1 in the adjacent shape. Both they are of equal lengths, both all sides are A plus B. I do the same for number 2, and I come this side, I remove triangle number 2, because they are all right angle triangles of lengths A, B, and C. Now I'm on number 3. If I shade off this, and I shade off number 3 like that, I do for the last time, I shade triangle number 4, I also shade triangle number 4 that side. So clearly, one can see that in the first triangle, what remains is a square. And this square is of dimensions C and C, such that if I want area of that square, it's going to be C squared. But let me move to the other rectangle whose area is the same as the first one. We can see clearly that there is a square whose area we said is A squared, and the second one B squared, such that if we combine them, because they are same shapes, if I combine A squared and B squared, it means the result is the same as what we have on the first shape. So I'm allowed to go adjusting and say, but in this square, which is of equal dimensions, A squared plus B squared is equal to C squared. That's all about the Pythagoras theorem. It says, in given a right angle triangle, the sum of squares of two shorter sides is equal to the square of the longer side. Now I'm still proceeding with the right angle triangle. We have proven it. So we are saying, given a right angle triangle, if I've got an angle theta, which is my angle of elevation, this side becomes my opposite side, and the side next or adjacent to the angle theta, we actually call it the adjacent side. Then the longer one, we call it the hypotenuse. So we have three trigonometric functions, which are sine, cosine, and tan. Now, Pythagoras says sine of an angle theta is given by opposite side over hypotenuse. Then cosine of angle theta will be adjacent side over hypotenuse. Then tan of angle theta is equal to opposite over adjacent. These functions are quite key in trigonometry, so it's important to remember them. Now, I'm coming to build up a proof to an identity. So I'm going to need a right angle triangle whose dimensions are similar to the ones that we had before when we were doing our proof that A, B are shorter sides and we have C. So the theorem will say A squared plus B squared is equal to C squared. But that's not our interest for this case. Our interest is going to be, can we prove that tan of angle theta is equal to sine theta over cos theta? Now, from these trigonometric functions that we have, where we say tan theta is opposite of adjacent. If we take that in mind to say, but for this triangle, tan of theta, which we said from the top, I'm going to say tan of theta is going to be opposite side, which is A in length, over adjacent side, which is B in length. Let's see if it's equal to what we have on the right. So the right, we are having sine theta. Remember, sine theta, we said is opposite over hypotenuse. So this is our opposite and this is our hypotenuse. So sine theta is equal to A over C, then divided by cos theta. So we are also going to divide that side. Cos theta is adjacent over hypotenuse, so that will be B divided by C, or that's B divided by C. Now, I'm going down to do a simplification to say, but what we have here is equal to, when we divide a fraction by a fraction, we turn the division to a multiplication, so that's A divided by C multiplied by, then we find the reciprocal of the fraction on the denominator, which is going to be C divided by B. So we can see clear that there's a C on the numerator, C on the denominator. So this will simplify to A divided by B. And if I can check carefully, this is exactly the same as what we have there. So it's true that tan of angle theta is equal to sine of angle theta over cos of angle theta. Then I'm doing the last identity that we have. I want to prove if it's true. So the last identity says cos squared theta plus sine squared theta is equal to 1. We want to test whether this is true. So what we will then do, I'm going to write it on the next page. I'm repeating cos squared theta plus sine squared theta. We are saying this is equal to 1. And we are going to use our right angle triangle, where we said of the two shorter sides, well, the longer one will be B, the shorter A, then we have the hypotenuse C. And we agreed from Pythagoras proof above that A squared plus B squared is equal to C squared. So let me check. If I say cos theta squared, well, cos is adjacent. So this is my angle elevation theta. So cos theta is adjacent divided by hypotenuse. So it's going to be B over C. And remember, we are squaring this, plus sine of angle theta. Well, sine is opposite over hypotenuse. So it will be A over C. And I'm squaring this. My interest is to check whether this gives us a result of 1. So I'm going to go my simplification with an equal sign on the left. Now, when I square, I get B squared over C squared, plus when I square the second part, that's A squared over C squared. So as I proceed with simplification, I've got a common denominator here, which is C. Sorry, let me erase this. Okay. Um, Let me proceed. C squared, but on the numerator, I've got a sum, which is A squared plus B squared. Fine, it's B squared plus A squared, but I just reverse it so that it's cleaner. Now, with what we have on the numerator, and if I'm to point it to what the theorem said from our proof, A squared plus B squared, we are agreeing is equal to C squared. So if I proceed with the simplifications, what it really and truly means is C squared on the numerator, because it's equal there, divided by C squared. And we know that when numerator and denominator are the same, the result is a 1. Thank you very much. If you're able to follow and make sense of this, I've got a strong feeling that your understanding of trigonometry can be improved. Goodbye.